In this episode, I will be delving into a deep and complex subject, which is the geochemistry and mineralogy of alumino silicate clays. But first, let's talk about soil minerals. Soil minerals are solid, naturally occurring inorganic substances that are homogeneous, have a definite chemical composition, and possess a characteristic crystalline structure. Substances primarily derived from the breakdown of rocks, such as the parent rock in the sea horizon of the soil, which makes up a significant portion of the soil mineral component that is formed by the weathering of bedrock in the D or R horizon. They play a crucial role in determining soil properties, influencing plant growth and impacting the overall soil fertility. These minerals are classified based on their chemical composition, crystal structure, and origin, with silicate minerals being most abundant. Soil mineralogists recognize two classes of minerals found in the soil. They are primary and secondary minerals. Primary minerals are minerals that have not been altered significantly since their formation in Earth's crust, such as silicate minerals like quartz, feldspar, and mica. Now, secondary minerals forms through the chemical alteration of primary minerals during weathering and during soil genesis or pedogenesis. These minerals are clay minerals like alumino silicate clays such as kaolinite, smectite, and illite. Other secondary minerals include non-silicates, such as oxides like hematite, as well as aluminum hydroxide minerals like gibbsite with the chemical formula AlOH3, and which is not a pure aluminum oxide, as well as sulfides and carbonates. Soil minerals are source of nutrients such as nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Clay minerals can cause the soil to have a high water retention capacity, and they increase the cation exchange capacity, as well as decreases the anion exchange capacity of the soil, because most clays primarily hold cations or positively charged ions because most clays are negatively charged. Minerals influence soil aggregation, porosity, and overall structure, affecting aeration and drainage. Carbonate minerals can influence the soil's pH, impacting nutrient availability and soil microbial activity. Quartz can be weathered to form aluminum-rich clay minerals over long periods of geologic time through the chemical process of hydrolysis, but it's a slow process because quartz is chemically stable at Earth's surface. Rainwater, also known as meteoric water, often made slightly acidic by dissolved carbon dioxide, breaks down the quartz structure by attacking chemical bonds and incorporating water into the mineral to form new hydrated aluminum silicate clays. Soil primary minerals like quartz provide structure and stability to the soil, and as the chemical weathering of feldspar occurs, potassium, calcium, and sodium are released, which are essential plant nutrients. And this is the product of millions of years of Earth's geochemical processes at work. Now let's delve deeper into micro-analyzing the geochemistry of different types of alumino silicate clay minerals. Most clays are hydrous alumino silicates, which are a group of minerals formed from aluminum, silicon, and oxygen, along with water molecules incorporated in their structure. These minerals are characterized by their layered structure, often consisting of tetrahedral, silica, and octahedral, alumina and magnesium sheets, which gives them their distinctive plate-like form and unique properties when moist. Now let's consider kaolinite. This is a hydrated alumino silicate clay mineral with the chemical formula Al2SiO2O5OH4. It is the stable end product of intense weathering of other alumino silicate minerals such as feldspar through the process of hydrolysis. Oftentimes, pockets of kaolinite are found within limestone or marl rock outcrops. Why is that so? Well, marl can be transformed to clay, but such transformation of marl to kaolinite clay is a very complex geological and geochemical process that primarily occurs through intense chemical weathering, particularly under hot and moist climatic conditions. Marl is a sedimentary rock composed of 35 to 65% of calcium carbonate, which is calcite, and the clay fraction of marl often contains expandable clays like smectite and illite, along with quartz and feldspar. Even though marl is composed of calcite and clay minerals, kaolinite forms from the decomposition of silicate minerals within the marl, and not from the calcite. The transformation requires the breakdown or decomposition of feldspar and other silicates, while the carbonate component is simultaneously leached away by acidic meteoric water or rainwater containing carbonic acid. Other aluminosilicate clays include montmorillonite, which is a member of the smectite group of clay minerals, which are characterized by their layered structure with a high capacity for swelling or expanding, and has a high cation exchange capacity due to water molecules and ions entering the space between the layers. Montmorillonite is one of the most common and economically significant smec-type minerals, often forming from the weathering and alteration of volcanic ash and being a major component of bentonite. Here is another interesting fact. These are known as swelling clays because their negatively charged layered alumino silicate structure allows them to absorb water, causing them to expand significantly. And this swelling and shrinking behavior is as a result of the presence of exchangeable cations and absorption of water molecules into its interlamellar spaces, which pushes the layers apart. Or a more easier to understand explanation is that cations and water molecules are able to move in between the units of Montmorillonite because of its easily expanded crystal lattice. Knowing about the geochemistry of Montmorillonite is especially helpful in the field of agriculture, so that farmers can evaluate and determine what crops grow best in this type of expansive swelling clay, and whether or not such soils are appropriate for certain crops to grow, and if they will give productive yields due to the fact that they can become extremely waterlogged and expand during the rainy season and crack during the drought. This swelling property is used in various applications like making barrier materials for landfills and drilling fluids. So what exactly are aluminosilicate clays, just to be clear? Well, they're basically minerals made up of aluminum, silicon, oxygen, plus a few other elements thrown in for good measure, like iron, magnesium, potassium. It's the specific arrangement of these atoms that makes clays so fascinating they occur as layered silicates. Imagine tiny sheets, almost like microscopic playing cards stacked together. These sheets can slide around, which is why clay feels so smooth and sticky between your fingers. But here's where it gets wild. The chemistry of these clays is all about swapping atoms. See, sometimes a silicon atom in the sheet gets replaced by an aluminum atom, or maybe a magnesium substitute in where an aluminum should be. These tiny substitutions create a charge imbalance, like a static cling on a sock fresh out of the dryer. Nature hates imbalance, so the clay picks up positively charged ions, like potassium. Sodium. This whole process is called cation exchange, and it's a big deal for soils. Water purification, agriculture. Let's zoom out for a second. Aluminosilicate clays are swelling clays which aren't just random dirt. They're the foundation for things like fertile soils. Because of their structure and chemistry, clays can hold on to nutrients, water, releasing them to plants when needed. That's why places with lots of clay tend to be great for farming. But they can also bind up contaminants, filtering groundwater, keeping toxins out of rivers. They're nature's tiny chemical filter, working quietly under our feet. And get this, the way these clays form depends on what's happening geochemically in the environment. Is it hot, cold, acidic, basic? What rocks are eroding nearby? All of these factors determine if you get kaolinite, elite, smectite, each with its own behaviors. Some clays swell when they get wet, others stay put. Some lock in nutrients, while others let them flow. So next time you see a muddy puddle, or work with a lump of clay, remember, you're touching the outcome of ancient geochemical battles. These minerals aren't just the building blocks of soil, they're architects of landscapes, silent custodians of clean water, and quiet partners in the story of life on Earth. Okay, so just to fine-tune this episode to make things clearer, here is an explanation to two terminologies I used earlier in the video, their cation and an ion exchange capacity. Firstly, cation exchange capacity, CEC, is the soil's ability to hold positively charged nutrients like calcium and potassium, while an ion exchange capacity, AEC, is the ability for the soil to hold negatively charged nutrients like phosphate and nitrate. Another terminology I used was hydrolysis, which is a form of chemical weathering, where water reacts with minerals causing chemical bonds to break and new minerals to form, like the transformation of feldspar within granite into a clay mineral. That's the hidden geochemical world of aluminosilicate clay minerals. If you enjoyed this episode of Geoscience Explorations and Explanations, subscribe to the Soil Mineralogist channel, and don't forget to press the like button and click the notification bell.